Hello class, in this exercise we have set of capacitors C1, C2, C3, C4 and C5, where the values of the capacitance of each capacitor are given. Also we have that the voltage VAB is equal 100 volts. Sometimes you're given such a circuit that doesn't contain a battery or a generator. Actually, it is a part of a circuit that definitely contains a battery or a generator. But just to make things easier, you can assume that there is a battery between A and B. So if VAB is equal 100 volts, then we can assume that we have a battery here, the positive pole connected to A and the negative pole connected to B, and VAB is equal 100 volts. The first thing that we should do with this circuit is to find C equivalent, where C equivalent is the one single capacitor that we can insert between A and B instead of all these capacitors and can basically do the same effect. So let's get started. If we look at the circuit, we can find that C1 is parallel to C2, which means that we can replace them by one single capacitor. Let's call it C12. So C1 is parallel to C2. Then their equivalent, let's call it C12, is simply C1 plus C2. Inserting the values of both in this equation, so this is 50 microfarads. Now we can keep this unit for now, the microfarads, and then we will convert it to farads later on when we need. If we look again at this circuit, we can find that C3 is in series with C4. So we can find their equivalent and let's call it C3,4. Whenever we have two capacitors that are in series, we can use this formula. C3,4 is simply C3 times C4 over C3 plus C4. And this formula is used only when we have two capacitors that are placed in series. Now, inserting the values of C3 and C4 in this equation, we get, after finding the values of C12 and C34, we are left with this figure. Observing this figure, we can see that C12 and C5 are also in series, so we will find their equivalent. Let's call their equivalent C125. We will use the same formula as before. And again, this formula is only used when we have two capacitors that are placed in series. Inserting the values, this is 25 microfarads. After finding C125, we are left with this figure. So C125 is parallel to C34. So we can find the equivalent, C equivalent between A and B for the whole circuit. So C34 is in parallel to C125. And let's find their equivalent. Let's call it C equivalent, which is simply their addition. So inserting the values that we already got, we get that C equivalent is equal 45 microfarads. After knowing that C equivalent is equal 45 microfarads, let's find the quantity of charge that is stored on the C equivalent. So we want to find Q equivalent. We can use this formula for Q equivalent. This is equal to C equivalent times VAB, where C equivalent, we already found it to be 45 microfarads. But when we want to use it in this equation, we have to use the SI unit. So we have to convert it to the SI unit, which is the farads. So this is 45 times 10 power minus 6 farads times the voltage, which is 100. So this is equal 45 times 10 power minus 4 coulombs, which is the unit, the SI unit of the quantity of charge. We know that the main purpose of the capacitor is to store electric energy. So let's find the electric energy stored in the equivalent capacitor. We can use one of these formulas to find W equivalent. Any of these formulas is correct. So W equivalent is equal half C times V squared, where of course C equivalent and VAB. So this is half times, here also we have to use the SI unit of the capacitance. So W equivalent is 0.225 joules. Now we want to find the quantity of charge stored on each capacitor alone. That is, we want to find Q1, Q2, Q3, Q4, and Q5. Now we cannot simply use this rule, Q equals C times V, because although we have the capacitance for each individual capacitor, but we don't have the voltage across each capacitor. We only have VAB. So how do we proceed? If we look at this figure here, we notice that C34 and C125 are across the same voltage VAB. So we can find the quantity of charge for those two capacitors by using the formula Q equals C times V. So Q34 is equal C34 times VAB. So taking the equation, the values of C34 and voltage, of course, we have to use the SI unit. Now, since C3 and C4 are in series, it means that they have the same quantity of charge, which is equal to the quantity of charge of their equivalent capacitor. So Q3 is equal Q4 equal Q34. Using the same equation to C125, we can find the quantity of charge for this capacitor. So Q125 is equal to C125 times the voltage AB. Now looking at this figure, C12 is in series with C5. It means that they have the same quantity of charge, which is equal to this quantity of charge, Q125. So we still need to find Q1 and Q2. In order to find Q1 and Q2, we have to find their voltage, which is VAH. We can find it from this figure here by using C12 and Q12. So we'll apply the rule Q equal CV for this capacitor. So Q12 is equal to C12 times the voltage VAH that we want to find. So VAH is equal After finding this voltage, we can apply the rule Q equals C times V for each of C1 and C2 alone. So for C1, this is Q1 and C1. Now we can get Q2 in two methods. The first method is simply using the same formula as here. There is another way for finding Q2. Looking at C1 and C2, and since they are in parallel, it means that Q1 plus Q2 is equal Q1, 2. So if we want to find Q2 in another way, this is Q1, 2 minus Q1. Inserting the values, we get that Q2 is 1.75 times 10 power minus 3 coulombs. So we can use both ways and these are equally correct. This is everything for now.